Wait a minute and then we'll start. You already know the polls.
Oh, yes. Sorry. I still should.
What's going on with the lighting?
What's that?
What's going on with the lighting?
Sorry, that's me. Oh, sorry.
Sorry,
That's me. I'm just trying to make sure this means.
Okay.
Yeah.
All right, morning everybody. And the usual story, name tags out, laptop shut. For some strange reason, I haven't memorized everybody's name yet. I know like 4 names. I know Julio's name, and I know Blessed, and I know Karthik, but typically by this time of the semester, I know half your names. All right, just fill out the attendance poll. And we're going to continue on the topic of recurrent neural networks. Can you guys see the board?
Yeah, but the poll is up.
The poll is not up? Oh my, where are my TAs?
The location is 1 hour 13. Okay, never mind.
All right, so it appears my TAs are not here. Just give me a sec. So I'll have the okay. Give me a sec. Well, if the poll is not up, that's too bad. Okay. So I guess we'll do without it now. But hopefully the other polls do come up, all right? So here's the story that we have so far. We found that in many problems we want to analyze time series data, and that we have to analyze the entire series before we can actually answer any questions, right? So here's Israel. Hey, Israel, the polls are not up.
Polls not up?
They're not up. Okay. So please. So 971. That's the attendance poll, right? So and so we found that one way of trying to analyze time series was through iterated structures, which were basically convolutional neural networks, but these have very finite memory. And so what we really want are recurrent structures which manage to capture long-term dependence and on the past. But then recurrent structures are not merely useful for analyzing time series. There are other problems too where they can show their might. So let's consider this problem. Suppose I want to build a neural network, a multi-layer perceptron, which learns to add 2 n-bit binary numbers, right? So now firstly, how large must this network be? How large must a network that performs addition of n-bit binary numbers be?
On that.
One depth? So if you, yeah, but how many neurons would you require? So you have to consider, this is essentially an XOR problem, right? And so you would have to consider the network is going to end up, if you're trying to train and build an MLP to add n-bit numbers, you're going to require, in the worst case, an exponentially large network. Now, suppose you want to train the network to perform addition. How much data would you need? You're going to see, you're going to eventually require every combination of inputs to ensure that you always get the correct answer, right? Yeah, but it is eventually does because addition is such a strange operation, right? And so you think it's simple, but it's not. And so to get assurance that you're going to that you're going to be correct every single time, you're going to have to see all of those, right? 2 raised to n. So in the worst case, you're seeing an exponentially large network and an exponentially large amount of training data. And of course, even after all of that, will this network, which can add 2 n-bit numbers to output an n plus 1 bit number, actually operate on n plus 1 bit numbers? No, it's done, right? On the other hand, if I did the same thing using just a recurrent network, that's my entire network. It's going to take the two inputs 1 bit at a time, and all it has to learn is to produce 2 outputs, the actual value and the carry. How large would this network be? It's 2 inputs coming out, 2 inputs going, 2 outputs. There may be 4 neurons in all. How much data would you need to train it? Not very much, right? A small amount of training data, and it's going to learn to perform this operation. So as you can see, just going from a MLP structure to a recurrent structure basically made the model exponentially smaller and infinitely faster to train. So here's another problem, the parity problem. Suppose I wanted to build an MLP that looked at an input and computed its parity. So how many is the number of ones even, or is it odd? How large would the network be? If you allow depth again, if it becomes deep, then it doesn't have to be exponential, but nonetheless, if for any fixed depth of network, it's going to be exponentially large. This is an XOR problem, right? And how much, suppose you decide to train this network to perform parity check, how much data would you require? You're going to, to ensure that you always get it right, you're going to have to see all 2 raised to n inputs. But then can we do this with a recurrent network? And what would the recurrent network look like?
Just be taking 1 input at a time.
I can just take 1 input at a time, right? And so I can always take the previous output, it goes back in, just like an ARCS network, and then you read the next input, and it's just a little XOR over here again. It's 3 neurons, right? So, and how much data would you need to learn it? 1 little sequence should teach it, right? So again, we have the same issue, same situation, where the actual amount of data required to train the network can be exponentially smaller, right? So I don't know. Is the poll up? Yeah. Okay, thank you.
Is it up? Yeah.
All right, that was an easy one. Anybody want to answer the first one? Karthik?
It's true.
Somebody on Zoom, can you answer the second one? Is there anybody on Zoom?
True.
True also,
True.
right? And so small prediction and classification problems that require very large MLPs and a large amount of training data could be solved using tiny recurrent networks that only require small amounts of training data. So recurrence is a very powerful concept beyond, and we use it all the time. You know, the rules of addition that you learned in school, they were recurrent, right? When you did Boolean, when you built your first Boolean circuit for whatever your digital logic class, if you took one, that was a recurrent network, and that's because recurrence is a powerful concept. And so the same thing also holds for convolutional networks. Convolutional networks, which are which have to look at a very large amount of history, would need an extremely wide window of input. They would have to consider an extremely wide window of input. But if you made it recurrent, the network is going to be very small. And so here's where we are. We have these recurrent structures, and they can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. And we saw that these could be trained using gradient descent and back propagation. Now, let me go back and analyze how these things behave. Now, consider this network. This is a convolutional network. Now, assume that the inputs are always bounded. Is the output always going to be bounded? If my activations are bounded in slope. Yes or no?
Yes.
Because the first neuron is going to see a sum of a finite number of inputs, right? And so an affine function of a finite number of inputs is going to be bounded if the inputs are bounded and the weights are bounded. So that output is bounded, and the same logic applies to every neuron downstream. The output is going to be bounded, which means for bounded inputs, the output is bounded. This network is what is called BIBO-stable. It's bounded input, bounded output. This is a term that often comes up in the analysis of recurrent models. It's a highly desirable characteristic. But now, what about this one? Is it necessarily BIBO? Why not? So you effectively have an infinite number of inputs, right? So it's not even the infinite number of inputs. It's just one input. Now, actually, I'm not quite right. If my output activations are all sigmoids, then I know that the output is never going to be greater than 1, so it's bounded. But then bounded by itself doesn't tell me anything. It's not enough for me to be bounded. It has to be informative. And for it to be informative, you don't want the output saturating. So as far as we are concerned, we can assume that the output is just a linear activation, and we can speak about boundedness for linear activation networks at the output. And in that case, we claim that there is no guarantee, but let's look at how it actually behaves. And to analyze how it behaves, it's sufficient for us to look at where the network actually differs from a convolutional network. And it differs in the recurrence, in the hidden layer, where the input passes through time. And now for my analysis, I'm going to assume that there's only one hidden layer, but the logic extends to any number of hidden layers. And again, the famous streetlight effect again, that it's very hard to analyze nonlinear functions. It's much easier to analyze linear and affine functions. So I'm going to look where there is light, and we're going to assume that this recurrence is linear for now. So what this means is that all activations are identity functions for the recurrent layer alone. Again, we are only analyzing the recurrent layer because that's where accumulation happens. If there's any unboundedness that happens, that's going to happen in the recurrent layer, right? And so we're going to say that the output of any one of these neurons is simply going to be the affine value that goes in, which is the weighted sum of the inputs plus the weighted sum of the previous hidden value. And I'm also going to assume that the bias is 0. Again, just to simplify analysis. It doesn't change the facts of the case. Now, let's consider, so here is my recurrence. I'm going to say HT is going to be some W times, this is the recurrent weight, HT minus 1 plus WX times XT. Now, can I write this in terms of HT minus 2? What would this be?
Expanding WH minus 1.
So this one is going to be WH times WH HT minus 2 plus WX XT minus 1, right? Plus WX XT, which is going to be WH squared HT minus 2 plus WH WX XT minus 1 plus WX XT, right? If I expand that out. Can I write it in terms of XT minus 3?
Yes.
So what would that look like? This is going to be WH squared times WH HT minus 3 plus WX XT minus 2. So when you expand that out, this is going to be WH cubed HT minus 3, right? Plus WH squared WX XT minus 2 plus WH WX XT minus 1 plus WX XT. So you can see how this, I can keep writing it in terms of histories further and further back. And so when I eventually write it out, that's what it's going to look like, right? And if I work it push that all the way back to the beginning of time, I'm just going to find that it's just given by this formula. There's the initial value, and then you can see that it's a weighted sum of all of the inputs. And this is why recurrence of one step is equivalent to a convolution that is infinitely wide, right? As you can see, this is just a convolution with infinite weights, except that the convolutional weights have a specific structure. And that's this one here, that if you look at the sum of the exponent of WH and the index of X itself, those two always sum to K. So the output at time K, the hidden value at time K can be written like so. That's going to be HK is going to be summation WH K minus I XI, right? That's about it. And I'm ignoring WX and I'm ignoring H minus 1 because these are initial conditions and just a transform on the input itself. So everybody with me so far, right? So now if I just analyze, if things are going to go bad or not, all I need to figure out is, will things blow up? And I only need to look at what happens to x0. So suppose I have an initial input at x0. Will the output blow up in response to x0? That's all I really need to see. Because if it blows up with response to later x's, then it definitely would have blown up with respect to x0, right? And if it doesn't blow up, for x0, it's not going to blow up for things that follow. So I just need to look at what happens to a single input at time t equals 0, and everything else can be everything else follows. If the output does not explode, if I just have a single input at t0, then it's never going to explode. Now, let's analyze this. If I have, is everybody with me on this one? That makes sense? Yeah. Agilia?
Not so much to me.
Okay, so look at this. I have it's going to be WH raised to K plus WH raised to K minus 1 X1 plus WH raised to K minus 2 X2 and so on. I'm assuming all of the X's are bounded, right? So if this blows up, the sum blows up, correct? If it blows up in response to any one of these guys, if this is bounded, that meant this has blown up, right?
Yes.
So this would have blown up too. Because you're just multiplying the blown up value with more WHs, right?
Okay.
Make sense?
Yeah, okay.
Yeah.
So you're assuming all the X's are bounded.
Yeah, all the X's are bounded, okay? So I just need to, this is bounded input, bounded output, right? So I'm just looking, so I just need to look at what happens to a input at the initial time instant. Now, let me ask this. Suppose I have this system, HT equals WH raised to times HT minus 1 plus XT. Then what is HT for, if all I have is X0 and no further inputs, then what is the actual response? It's there on the board, right? If all I have is X0, what is the actual response?
Input response.
Go ahead, yeah?
So your input response, H from negative 1?
So look at this, from this value that I've erased, right? This is only going to have a value at I equals 0, correct? So this is going to be WH raised to K X0. That's all you're going to have, right? Everybody with me? So now let's consider the scalar case, where X is a scalar and H is a scalar. When will this blow up? When will this blow up?
Can you repeat? What the conditions were?
X is a scalar, H is a scalar. So when will H blow up with time?
When W is unbounded.
When W is unbounded?
Or W is greater than 1.
If so, if W is greater than 1, implies, HK tends to infinity as K tends to infinity, correct? Pretty much, because WH raised to K is going to go up. What happens if W is less, WH is less than 1? It's just going to go to 0. What did not happen? The actual value of X was forgotten, right? Either the system blew up or X was diminished without a trace, right? And so this is what you're going to find, that for a single input at time 0, if you follow the response of the system, response is either going to blow up or it's going to go away. It's going to completely disappear. This is for a scalar case. What happens for if WH is a vector? It's very easy for us to analyze what happens when W is a scalar. X is a scalar and H is a scalar. But when all of these are vectors, how do you analyze it? We can look at the eigenvalues, right? So I can say, again, the same thing. Now remember, this is recurrence. So the W matrices are all square because the number of hidden components is going to be the same at every stage in the network. And so I can write W, I'll drop the subscript H, as some U lambda U inverse, right? And what is W raised to K over here? What's it going to be? It's going to be, you know, U lambda, U inverse, U lambda, U inverse K times. These will cancel out, right? And so the whole thing is simply going to become U lambda raised to K, U inverse. Everyone with me? Right, okay. So let me write this out in proper matrix form. W raised to K is going to be U times lambda 0, lambda 1, lambda n, whatever the dimension is, times K, U inverse. Correct? I just wrote out the eigenvalue matrix. All the other eigenvalues are 0. Right? And so this I can write again. So assuming that they are in order of decreasing value, and that lambda 0 is the largest one. So that's going to be lambda 0 raised to K times U times 1. This is going to be lambda 1 over lambda 0 raised to K, lambda 2 over lambda 0 raised to K, and so on, 0, times U inverse, right? What happens to this matrix as K tends to infinity?
Just the one term will remain.
As K tends to infinity, what happens? Yeah. Just the first term, right? Because all the rest of them are less than 1. So as K tends to infinity, this becomes, I'm writing topsy-turvy. This is going to be lambda 0 raised to K, U, 1, and then all zeros, U inverse. Right? So what does this depend on? The largest eigenvalue. And now, if the system, under what condition will the system response explode?
Your first eigenvalue is
If the first eigenvalue is larger than 1, then the hidden vector H is going to blow up. And if the first eigenvalue is less than 1, it's going to diminish and go to 0. Right? Everyone with me? So basically, here's what we have. I have a bunch of slides, but then I think we've kind of explained the concept. And so I have a couple of cases over here where in the first case, the largest eigenvalue is 0.9, and you can see how the whole thing vanishes. In the second case, the largest eigenvalue is 1.1. You can see how it blows up. When the largest eigenvalue is 1, you can see an oscillatory behavior on the left-hand side and a smooth behavior on the right-hand side. Why do you see the oscillatory behavior on the two plots to the left? Anyone? Complex, right? Eigenvalues can occur in complex pairs. So this is a case where I have complex conjugate eigenvalues. So I have two eigenvalues which are both 0.9, or two eigenvalues which are both 1.1 in magnitude, but they're going to interact. So it's not going to go down smoothly. It's going to sort of oscillate down or oscillate up. But nonetheless, the whole thing is going to blow up, right? So I'm plotting the magnitude. So here, this is a response of the hidden vector H to a single input, which is a vector of 1s at time 0. Okay, and you can see how the thing sort of either vanishes or blows up. Now here we have assumed that the hidden activation is strictly an identity matrix, linear. There is no hidden activation function itself. And when we have no hidden activation function, we observe that if the weight matrix has an eigenvalue, largest eigenvalue greater than 1, it's going to blow up. Otherwise, it's going to vanish. What doesn't happen is any retention of the value of x0 itself. It forgets what x0 was because it either blows up or vanishes, right? Now, So the lesson here is that in linear systems, long-term behavior depends entirely on the eigenvalues of the recurrent weights matrix. If the largest eigenvalue is greater than 1, the response is going to blow up. If it's less than 1, the response will vanish very quickly. Complex eigenvalues can cause some oscillatory behavior, but to the same overall trends. And the rate of blow up or vanishing depends only on the weight matrix. It does not depend on the input. Now, everyone with me? Right, okay. What happens if I put in an activation function instead of just having something linear? Because that would be a natural question that you would ask. Okay, this is linear, but in a real neural network, I'm going to have an activation function. How does it behave? So here's what happens when I toss in a sigmoid activation function. Here I've done this for, again, a scalar, the scalar case, where the hidden value is just a scalar. And so the recursion is going to give you scalar values. And I have a single input at time 0. And here's how the plot is. I have a sigmoid activation, and with this is in the recurrent hidden layer. The hidden value at time t is the sigmoid activation applied to w times ht minus 1 plus xt, and plus b, because it's an affine value, right? So the affine value also has the bias. Now within this plot, within any figure, I have a weight value, and each of the 5 lines shows you the responses for 5 different values for the bias B. The figure making sense? Right, okay. So this row shows responses for networks where the weight is 0.9, and each of the 5 lines is the response for the 5 different values of the bias. This first plot, the second row is the same thing for weight 1, and the one on top is the recurrent response for weight 1.1. And the first column is the response that you get when the initial x value is minus 0.5. The second column is the response that you get when the initial x value is 0. And the third column is the response when the initial x value is plus 0.5. Okay? Now, for memory behavior, what we are interested in is what happens after several time steps. And the x-axis within each plot shows time. And what do we see? In every case, after about 10 time steps, the plot is identical, right? So is there any information about x remaining? Regardless of the value of x, it ended up in the same place, right? And where it ended up depend on? Just the bias. Nothing changed, right? So if I have sigmoid activations in pretty short order, everything is forgotten. All that's remembered is a network parameter itself, the bias, right? So maybe this is a problem of the sigmoid. Let's try other activations. Here's a tan H, same case, right? And what do we find here? You find that within any row, the figure is the same at the end. The vertical scales are slightly different, so they may look different. But within any row, you will find that the values of these curves are the same after about 20 time steps. Now, there is a difference between the 3 rows, which means that the final value that's remembered is a function not merely of the bias, but also of the weight. But what it is not a function of is the input x. Make sense to you guys? Right? So once again, what do we find? Is the recurrent network actually remembering things? No. Now, you do find that in the case of the tan H activation, it's remembering it for slightly longer than in the sigmoid, where it was forgotten in 3 time steps, which is why in recurrent networks, in the hidden layer, we use tan H activations. They tend to keep things alive a bit longer, and that's because they're bipolar. They go from -1 to 1, as opposed to going from 0 to 1 for the sigmoid. But regardless, what we find is what is remembered is not a function of the input. What is remembered is a function of the network parameters. So maybe sigmoids and tan H's are not great. Maybe I should try ReLUs. But what's the issue with ReLU? A ReLU is basically an identity activation. Things are either going to blow up or going to die. It depending on what the value is, right? And that's exactly what we see once again over here, that it's not going to, it doesn't really remember the value of x. So now maybe things are different when you actually consider vectors instead of scalars. So let's go and check. You find exactly the same behavior. So in this case over here, these two plots, the vertical axes are slightly messed up. So here I have two different, in the two rows show the responses for two different two different x zeros. And you can see that after about 10 time steps, both of them have the same response, right? That's for a sigmoid. This is for a tan H. Again, after about 10 time steps, both of them have the same response. In the case of the ReLU, things blow up or vanish. So the lesson remains the same, right? And the lesson is that what is remembered, quote unquote, does not depend on the input anymore. It only ends up depending on the parameters. And it also, how long it holds on to things, it also depends on the activation, right? But that's it. And so this is for a different H value. But the lesson remains the same, that the standard recurrent architecture has really poor memory. The best case is for the tan H activation, and even there it remembers things for maybe half a dozen time steps before it basically loses track of what had been input. Now, you can do we are looking for BIBO stability. You want the things to not blow up. You don't want things to die. So you want things to sort of be remembered. And if you want to do a formal analysis, you have to consider Lyapunov functions and Roots criterion and things like that. And the math gets to be a little tedious. But for our purpose, we don't really need to go through the math. The lessons that we saw should be telling enough. Because when you analyze linear activations, it tells you what will happen. And just adding a nonlinearity on top of it doesn't really change the story. So the lesson we have is that bipolar activations like tan H have the best memory behavior, but the behavior actually still depends only on the parameters. Specifically, it depends on the bias, and it depends on the eigenvalues of the recurrent weight matrix, right? And the best case memory is short. The memory behavior is exponential, and that things are forgotten exponentially fast in every single case, except when the eigenvalue is 1. Is it sufficient for one eigenvalue to be 1? So let's go back over here, right? What if lambda 0 is 1 and the rest of them are not? Then what happens? The only thing that remains is the first eigenvector. All the other components are going to be zeroed out. So it's not even sufficient for one eigenvalue to be 1, right? Or some subset of eigenvalues to be 1, because if you do that, then all that's remembered is whatever is in the subspace spanned by those eigenvectors, and everything else is forgotten, right? Everybody with me? Yeah. So, pull 2. Okay, 10 seconds, guys. Right. Okay. Can someone on Zoom tell me about the first question? Is the first statement true? The first statement of the first question, is this true? Zoom?
Yes, it's true.
What about the second one?
It's true also.
The third?
True also.
And the fourth?
False also.
And
False.
okay, folks in the room, what about the second question? Is the first statement true? Second? Third? And the fourth? Right? So it's a lovely lesson, right? We just built up this whole idea of recurrent models and state space models and so on. But when you look under the hood, the one thing it's not doing is the one thing that you wanted it to do, which is kind of a bummer. So the story so far is that recurrent networks retain information from the infinite past in principle. In practice, they tend to blow up or forget. And if the largest eigenvalue of the recurrent weight matrix is greater than 1, then the response may blow up. If it's less than 1, it's going to die. And even if the largest eigenvalue is 1, everything corresponding to the subspace spanned by the remaining eigenvalues is going to be forgotten, right? So the memory of the network also depends on. So the memory of the network depends on the parameters of the activation of the hidden units. So sigmoid activations saturate really quickly. ReLU activations tend to blow up or vanish. And tanh activations have slightly better behavior, but they still have this tendency to forget. So the main issue is the weight matrix, and a secondary factor over here is the activation function. Okay. So here's the lesson so far. Recurrent neural networks are excellent models for time series, for time predictions, or tasks, or time series classifications, or sequence generation in principle. In practice, what we find is that the memory isn't all that great. There's a second issue, and the second issue is not specific to recurrent networks, but to all kinds of networks which get deep. Now remember, a recurrent network is really a very deep network. Why is it a deep network? The path from the first input to the last output can be arbitrarily long, and that's the depth of the network, right? And so all really deep networks have a challenge, and that has to do with training, which is the gradient of the error with respect to weights. This can be very unstable. So to see how this works, I'm going to speak about a standard deep MLP, but the same thing applies to recurrent networks also. When I have an MLP, let's ignore the biases for now because they don't really change the story, okay? And the first layer, I compute a weighted sum of a linear transform of the inputs or an affine transform of the inputs, apply an activation. Then I compute an affine transform of that output, apply an activation, and then compute an affine transform of that output and then apply an activation and so on. So a recurrent network is, a multi-layer perceptron is basically a nested function, a deeply nested function, right? And so the whole thing can be written as Fn, where this is the final layer activation of Wn times Fn minus 1, where Wn is the weight matrix for the final layer. Fn minus 1 is the activation of the penultimate layer of, again, some weight matrix times the previous activation and so on. And the divergence between the output of the network and the desired output is also a nested function. It's a function of the output of the network itself. Now, I can write down the derivative rules. I've written them in kind of crappily, but the way, because I've written them as df over dx, whereas this is really bad notation, we know, when you're speaking of vectors. But I'll use the abuse of notation for now, just to explain the concept. And that's this. If I have every layer of the network had this form, y equals f of w of x, right? where X was the output of the previous layer, and this was the weight that was applied, and then you had, and that gave me the, once I applied the activation F on it, it gave me the output of the current layer. So if now, anytime I have something of this kind, if I want dy over dx, I can write this as dy. Let me write this as, write z equals wx. So it's dy over dz times dz over dx, right? Is it what I've got? Or let me say y of g of x, just to show you how nesting happens, okay? So I can say z equals w times g of x. So this is going to be dz over dg times dg over dx. Everyone with me? And what is the central term? What is dz over dg? That's just the w. That's just the w, right? And so I can write this as dy over dz times w. Everybody with me? Okay, now what are these? These are, z is a vector, x is a vector. So what are these? Although I've written them as dg over dx and dz over dy over dz, these are actually Jacobians. Are they not? Okay, so I can write the whole thing like so. The Jacobian of g with respect to x pre-multiplied by w, pre-multiplied by the Jacobian of y with f with respect to z. So everybody with me? Okay, so this is the key piece. Once you remember this, then I can write out the Jacobian of the derivative of y with respect to x is going to be the Jacobian of f with respect to z times w times the Jacobian of g with respect to x. Okay? Stay with me. Now, I have the divergence. The divergence is a nested function. So using exactly the same principle, if y is my divergence over here, the derivative of the divergence with respect to any intermediate output of the network, which I'm calling fk, right? This is going to be the derivative of the divergence with respect to its argument, which is the output of the network itself, right? Times the Jacobian of the output layer, times the weight matrix of the output layer, times the Jacobian of the penultimate layer, times the weight matrix of the penultimate layer, and so on. We saw this many classes ago. Yeah, this should mean you. Everybody with me? Yeah. So to understand what happens to this derivative, we just have to understand what happen, how these Jacobians and these weight matrices work. So you start off with the derivative. Again, these derivatives are row vectors, right? Remember? So you start off with the derivative of the divergence with respect to the output of the network. That is transformed by, what's it transformed by first? Guys, the last layer is Jacobian, right? So this derivative of the divergence is first transformed by this Jacobian, and then that result is transformed by this weight matrix. That result is transformed by this Jacobian. That result is transformed by this weight matrix, and so on. Now, what do these Jacobians look like? So let's first see what the Jacobian of an activation function looks like. If I've got in a typical layer, let's say I'm applying some kind of activation function. If it's a scalar activation, meaning if I have an independent activation function being applied to every component, then the Jacobian is going to be a diagonal matrix, right? And this is going to be f prime of z1, f prime of zn, and the rest will be 0, right? That's what the Jacobian matrix is going to look like. Everybody with me? Right. And what about these values? What do they look like? What are these? They are slopes of your activation function, right? What is the largest value the slope can take for most of your activation functions?
Really?
What activation functions do you use?
Activation function. Okay.
Right? For ReLU, it's 1. For tan H, it's 1. For sigmoid, it is? The largest value is 0.25, right? And typically, is it actually going to be 1 or no, right? In a very small number of cases, it's going to be 1. For most components, you're probably going to be less than 1, right? So what happens if I multiply a vector? So let me call it this any vector. This is a row vector V. If I multiply this by a Jacobian, what happens to the length of the vector?
Oh, you're saying it shrinks.
It should shrink. Every single component will either retain its value or become smaller. Correct? And so, as a result, these are all Jacobians. Jacobians have this form. And if you look at typical activation functions, the largest value of the derivative is going to be 1. Typically, it's going to be less than 1, which means that as we go back in the layers, these Jacobians will shrink the vector progressively, right? Everybody with me? Okay. What is the other component in this chain of derivatives? The weight matrices. What happens if you multiply something by the weight matrix? It will either, okay, it won't uniformly shrink it, but here's what happens. So consider a bunch of vectors on a perfect circle, all the vectors on a circle, right? So I'm just interested on the circle itself. If I transform this using a weight matrix, what is the output shape going to look like? If I multiply, yes, go ahead. You gestured correctly. Is it going to remain a circle? What will it become? It's going to become an ellipsoid. Okay? Because it's a linear transform. It's going to stretch or shrink and maybe a bit of rotation, right? And so let's assume for now that the radius of this circle is 1. Okay. So what is the largest value amount by which a vector can be stretched by this transform? What is the largest amount if you look at the picture, right? It's going to be this.
Yeah.
Correct? And what is the smallest amount by which it can be shrunk? This guy. Do you know what these terms are?
Major axis, minor axis.
But what is it for the matrix?
Oh, this is
These are the singular values of the matrix, right? So the largest singular value of a matrix is how much is the largest amount that the matrix can stretch a vector by. The smallest singular value of the matrix is the smallest amount that it can stretch or shrink it by, right? And so if I take a typical matrix, and if I plot all of the singular values in descending order, then you're going to find that if these are my singular values and this is the rank, you're going to find it just falls off really fast. If I take a 1000 cross 1000 matrix, maybe I get 10 singular values which are greater than 1. and pretty much everything else is going to be less than 1. So now if I transform a vector by this matrix, what happens? Any components that lie in the directions that align with these singular values, they're going to shrink, right? And there's a very small subspace corresponding to the singular values that are greater than 1, where the vector will actually expand. Does that make sense, everybody? And so over here, what we find is that this multiplication by the weights is going to expand the vector along directions where the singular values are greater than 1, and it's going to shrink it along directions where singular values are less than 1, and the singular values that are less than 1 for any random matrix, they're going to dominate. In fact, often all of the singular values are going to be less than 1, right? Unless you actually take great care. And so if I repeatedly multiply a vector by a matrix, right, what happens? The components that are aligned to the singular values greater than 1, they're going to explode. And the components that are aligned in different directions, they're going to vanish. And so, but then here's the strange thing, right? The vector, these are singular values. These are not eigenvalues. They're going to get rotated. So if you initially start off along a direction that's aligned with a singular value, let's say 1000, it will rotate to a new vector, new position. At the new position, the singular value is no longer going to be 1000. It's going to be less, right? So eventually, if you randomly keep multiplying this, almost everything will vanish and a small number are going to blow up, right? And so if I look at this collection over here, when I see how the derivative propagates backward through the network, the derivative within each layer, it's going to be transformed by the product of the Jacobian and the weight matrix. And what happens to the derivative depends on the singular values of this product, the product of the Jacobian and the weight matrix. The weight matrix is bad enough. The Jacobian matrix is almost definitely going to be shrinking the singular values further, right? And so and the manner in which it shrinks it is not fixed. It depends on the input, because f prime depends on the position, right? And so as you keep going back through the network, at the output, your derivative vector might be very long and very large. But as you keep stepping back, it's going to keep shrinking in values, except for a small number of components, a small number of directions corresponding to the singular values which are greater than 1, which are consistently greater than 1 through the network. Those are going to blow up. That makes sense, right? And so you're going to end up with vanishing and exploding gradients. So here is a little experiment that we ran. This is on the MNIST data. And this is at initialization. Remember, at initialization is when your derivatives are expected to be largest, right? And this one has something like 19 layers. The output layer is shown at the top, and the input layer is shown at the bottom. And I have all of the neurons laid out left to right. And the grayscale shows the magnitude of the derivative. And what do we see? This is the collection of derivatives over a mini batch. And as you go down through the network, by the time you get to about the 5th layer, all the derivatives are gone, right? This is for an ELU activation, which is a pretty good activation, right? This is for a ReLU. And if you compare the two, you see that in the case of the ReLU, the activations vanish even faster, right? This is for a sigmoid. The activations vanish faster still. Tanh, not very different. So this is for a mini batch. I can do this also for individual instances, and you observe the same pattern in that close to the output layer, the derivatives are actually quite large. But then as you go back through the network, because of the properties that we just saw, then derivatives keep getting smaller and smaller. And by the time you get to the input layer, there is no derivative left at all. Now, it's not true that there is no derivative left, because if I set the derivative as 0, this tells me that I could have changed the input any amount and the output would not change. Is that true? No. So what do you think is happening? Changing the input does change the output, but all of the derivatives end up being concentrated in a tiny number of components. So there are a small number of components where the derivatives are simply going to blow up, and in all the others, the derivatives are going to go to 0, right? And is this behavior we want? No, because if the derivatives are 0, you're not going to be learning those parameters. If the derivatives are blowing up, you're going to learn crappy values, right? Because we know that that's when you get oscillatory behavior in your optimization. And so we find ELU activations maintain gradients longest, but in all cases, gradients have effectively vanished after about 10 layers. And this is true for both batches or for individual instances because the behavior is the same. I've considered the batch because we know that the Jacobians vary by input, right? So if I average this over many inputs, maybe you get decent behavior. No, you do not. By the time you get to the 10th layer, things have vanished, right? So our story here is that recurrent networks are supposed to retain information in principle from the infinite past. In practice, they are really poor at memorization. The hidden outputs blow up or shrink to 0 depending on the eigenvalues of the recurrent weight matrix, but the memory is also a function of the hidden activations. This is during inference, but during training, you have an even more difficult problem that during inference, it's the memory behavior of the network that is bad. During training, you just don't get signals to update the models with. So this fact here is true for all deep networks. For deep networks, the gradients are going to vanish as you go back through the network, and recurrent networks are really very deep networks. And so you're going to get vanishing gradients as you go back through the network, which means that it's really not going to learn long-term behavior because the gradients have vanished. There's no way that it is ever going to figure out that something that happened here caused some perturbation 20 time steps down the line, whereas in real life that always happens. And so we have the situation where gradients get forgotten during training and memory is bad. And why do these two problems happen? Again, it happens because the weight matrix may have eigenvalues that are not 1, and any kind of activation function is going to end up causing fading of gradients and fading of memory, right? So on the other hand, it's maybe we say maybe we're okay with having a finite duration of memory, but is that really the case? Not true. Any questions on Zoom?
No.
Okay, 10 seconds, guys. Thank you. So, folks on Zoom, is the first statement in the first question true? Anyone on Zoom?
Yes.
Second one?
Yes.
Heard?
True as well.
And the fourth?
Also true.
Right. So basically, the derivatives for most parameters become vanishingly small as we backpropagate the loss gradient. And for a small number of parameters, it could blow up. The derivatives would be more stable if the recurrent weights had all singular values equal to 1, right? They would also be more stable if the recurrent activations were identity transforms and didn't have this habit of shrinking the gradient as it passed through the Jacobian, right? Now, what about the second question, folks in the classroom? Is that first statement true? Second?
Yes.
Third?
Yes.
And the fourth?
Yes.
So here you go, right? So the memory of recurrent layers is limited because the recurrent weight matrices do not have all eigenvalues equal to 1. They're also limited because of the nonlinear activation functions. And so the memory would be more stable if all the weight matrices had all eigenvalues equal to 1. It could be more stable if the activation functions were identity transforms. Everybody agree with all of these statements? Okay, now let's go back and redesign our recurrent neural network. Can you help me? Okay, go ahead, Josh. You have promised. Yes. So now here's the behavior that's really important, right? Let's think of a neural recurrent network or any network that's analyzing, for instance, some code, parsing code or generating code or what have you. How long do you have to remember things? You have to remember things until it's okay to forget them, right? The how long you must remember them should not be a function of the network, the weights or the activations. It must be a function of the input and the input alone. So for example, if I'm analyzing code, if I have a curly brace that's opened, I must remember that this curly brace was opened until I encounter a closed curly brace. Not any odd closed curly brace, but the matching closed curly brace. And when can that matching closed curly brace happen? Is there a fixed time? It can be arbitrarily far away, right? It can be thousands, millions of characters away. And you're going to have to hold on to this idea until you actually encounter it. That makes sense to everybody? So, okay, given this, we want memory behavior that only depends on the input, or the memory behavior that depends on the input. And we find that the actual memory behavior is restricted by weight matrices and activations. So how can I solve this problem? First, does everybody agree that a weight matrix is a problem?
Yes.
So what should I do? Get rid of it. Thank you, right? So this is going to be my network. And so now I've got rid of the weight matrices, right? Do we agree that activation functions are a problem?
Yes.
What do we do with them? Get rid of them. Thank you, right?
Yes.
Lovely. But then how do we modify what's in memory?
Bias.
Bias? But no, you want the input to respond. I've opened a curly brace. I want to shut it when I see a closed curly brace. How do I take care of that? Go ahead. Well, no, but I have to. So here's the thing, right? What I would need is something of this kind, which checks if there's if a curly brace has happened, right? And I want something that directly analyzes the input and modifies what's in memory based on what has been observed in the input, right? Is it sufficient for it to analyze what's been observed in the input? Does it matter that you've seen a closed curly brace if you have never seen an open curly brace? No, right? So what does this mean? this guy, this is a pattern classifier, right? It's going to be looking at the input. What else will it be looking at? What's currently in memory, right? And think of code. What else would you be looking at? I see a closed curly brace, but it could just be in the comments, right? So you're going to be looking at some other stuff. This makes sense to everybody? And so that's how we're going to change life. You know, mystery and magic, right? So the memory depends on the behavior of these underlying terms. We're going to get rid of it. We're going to eliminate the weight matrix. We're going to eliminate the activation function. And we're going to change the network such that the behavior of what's in memory is going to be modified based only on what it sees in the input. That makes sense to everybody? And where the logic actually comes from. So this logic is very pretty, right? This is the basis of your LSTMs, long short-term memory networks. You have this line in between, which is where the memory is stored, and it's carried through uncompressed. It's carried through just as is. There are no weights. There are no nonlinearities. The only thing that manner in which it's changed is through these gates, which analyze the input. And the gates say, okay, I've seen pattern 1. Pattern 1 is in memory. Have I seen pattern 2, right? And so now, what's in memory is not being transformed by any nonlinearity. But for neural networks to actually make sense, you want nonlinear transforms. So you're going to separate the memory from the nonlinear transform, and you would put what is in memory through a nonlinear transform before you actually begin operating on it, right? And so these gates are going to be looking at input, looking at whatever hidden state, other stuff, and maybe what's also in memory. Basically use as much context as possible to figure out whether what's in the memory must be changed or not. Okay. And that gives rise to our so-called long short-term memory network. If you ever wondered where that crazy structure came from, hopefully you see some light, right? Okay. I'm using some figures that I've stolen from the web. I've stolen liberally from the web throughout this course. And I've tried to attribute my sources, but I don't always succeed because sometimes you don't even know where it came from. The person you stole it from might have stolen it from somewhere else, right? So this one is your standard recurrent neural network. Okay, I've just shown what happens at one time step. We like to think of it in terms of cells. You have the previous hidden history. You have the current input, the combination of the two output through an activation, typically at tanh, and passed on downstream, right? And to layers above. So instead, the LSTM does something like this. Now this structure looks crazy. But then if I break it down, it's actually very simple. The key component is a remembered cell state. And that remembered cell state is the memory line, which has no weights and has no activation functions. So that's what we call the constant error carousel. I don't know why we call it that. I didn't come up with the name, but we'll stay with it, right? So it's a CEC, and it carries information through, but it's only affected by gates. What's in the memory is only affected by external stimuli, which are derived by analyzing the input itself. Now, these are obtained through gates, which are simple sigmoidal units with outputs in the range 0 to 1, which tell you whether something that's in memory how much what's in memory must be shrunk by. And so you have multiple gates. You have something going through memory, and then the first thing you have is something called a forget gate. So for example, let's say I have a memory line which says I have seen 8 curly braces so far. Then when I see a closed curly brace, I must reduce that number from 8 to 7. And so I'm going to have a gate which is going to be searching for closing patterns, so to speak, which shrinks what's in memory. But then that's about forgetting, right? But then afterwards, I also want to say, okay, hey, I've seen one more curly brace, open curly brace. Remember, the patterns that cause you to forget what's in memory can be different from the patterns that cause you to increment what's in memory. So that's why you need 2 separate structures over here. And so you can say, hey, I'm seeing another open curly brace. Should I be incrementing it? And so you have a pattern detector shown by the tanh unit, but then that open curly brace might just happen to be in a comment section, right? And so you have a gate also controlling this one. And the product of the two that you have here, the product of what comes out of the pattern detector and what is computed by the gate modifies the memory line. Now this is additive. If you make them all multiplicative, the behavior becomes kind of indeterminate. So the forgetting and incrementing are done using two different operations. Forgetting is multiplicative. You directly multiply it with a gate. Incrementing is additive. You see something and you add stuff to the memory, right? And then, of course, finally, what comes out must be passed through a nonlinear transform for it to be operated on by the rest of the network, because you want non-linearities. And the nonlinearity over here is the tanh. So the hidden memory state is passed through a tanh, and this is the actual hidden state, and that is operated on by yet another gate, which is called the output gate. Now, I haven't quite understood why we need an output gate. It seems somewhat gratuitous to me, but apparently it makes a difference, right? So, and so this is the entire structure that you've got. Now, what do the gates actually work with? The gates work with what's the current input, what is currently in memory, and what also the current hidden state. So now the hidden state and memory are basically two versions of the same thing. But just because we like to have lots and lots of parameters, this network actually combines both in its analysis. So here's the complete LSTM unit. And I have time for a poll. I may go over by a few minutes, guys. Bear with me. Actually, since we're going to be running out of time, why don't we just take these questions straight? The first statement, true or false? True, right? They stabilize memory by eliminating problematic recurrent waits and activations. Second one, true. They update the memory based on patterns detected in the input and the current context of what they already remember. The third one, true or false? In the absence of external cues, nothing changes, right? So they could remember forever. They're suited to building pattern analyzers requiring long-term memory, true or false? Or true, right? Beautiful. And so you can see how we come up with this lovely modification, which sort of solves all of our problems in memory. So if you want to use capture things in memory, this is what you use. And here's the sequence of operations. These two gates, the input gate and the forget gate and the input gate, are computed from what's currently in memory, the current hidden state value, which is the non-linearly transformed memory value, and the current input. Then from these, you also compute the pattern detector computes its own output, and that output is further modified by the input gate to give you the updated memory out here. The output gate actually operates on the updated memory and transforms the memory value to compute to generate the hidden state. So I have some code for this. Take a look. Okay. Now I'm quickly going to go through some back propagation rules for this one, and you'll see that back propagation rules are kind of painful, right? So if I begin trying to compute the derivative of the divergence with respect to, say, CT, here are all the chains of influence that I have to consider. This one, this one, this one, this one, this one, right? And there are a whole bunch that I've missed. Similarly, if I want to compute the derivatives for HT, here's 1, 2, 3, 4, 5. The number is arbitrarily large, right? So trying to write out the math for this one is not going to be easy. It's going to be quite impossible. So what do we do when you can't write the math for derivatives? Just go back to code, right? When you look at code, things are very, 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 very simple, right? Math is best done with by computers. So just give me the 2 minutes for this one. Here was my forward code. So I can think of each memory structure as a single cell. It takes the current input, or whatever comes in from the bottom, and then it's going to take in the current memory and the current hidden state value, and then it's going to use it to perform its computations. So it first computes an affine term for the forget gate, then computes the sigmoid from the forget gate for it, computes the affine term for the input gate, computes the input gate value, computes the affine term for the pattern detector, computes the pattern, and the memory is updated by first multiplying it by the forget gate and then adding the weighted pattern that was detected. And then using this, it computes an affine transform and then computes the output gate, which multiplies the transformed memory value and then passes it out. So this is the sequence of operations, right? To compute derivatives, I just had to flip it. I have to remember, it's backprop. I go from the bottom to the top, right? So here, what would be coming back are the derivatives for the terms that go out. And from those, you should be computing the derivatives for all the terms on the inside. And so if you look over here, let me take the last operation over here. The last operation multiplied the nonlinear transform of the memory. This one, the nonlinear transform of the memory with the output gate, right? So when I'm coming back, I would expect to have the derivative for h. So dO is simply going to be dH times tan. And then the derivative for C is going to be the derivative for tan times the derivative for the activation function. You can see, I'll leave this as an exercise to you. Just go back and look at the code. And you can see how all I have done is take each line of code and decomposed it step by step by step and worked my way back to compute the derivatives. And I didn't have to think about the math. This will work, right? We have a handout for this called How to Compute a Derivative. Please take a look at it. And then, so one final bit. That network, the model that we saw seemed rather complicated. So there have been any number of attempts at trying to simplify it. One of them is this gated recurrent unit, right? Which answers some of the questions for why we want so many things. So here they make an assumption that, if you're forgetting something, then that same pattern is not going to be incrementing the memory. If you're incrementing the memory, and that same pattern is not going to be used for forgetting. So you used a single gate for performing both the forget and input operations. Then second, why bother to carry both a memory and a non-linearly transformed version of the memory? Just retain the memory and perform the nonlinear transform on the fly, right? And so this one gives you the gated recurrent unit. And there are any number of models of this kind. And how are LSTM units used? In your recurrent model, the green box now just becomes an LSTM unit. That's it. Nothing changes, right? And so you can also use it for bidirectional networks and all the rest of it. So thank you. Just to close out, LSTMs are an alternate formalism where memory is made more directly dependent on the input rather than model parameters through a constant error carousel with no weights or activations. And these do not suffer from a vanishing gradient problem, but as we will not explain, but I can discuss this on Piazza, they can make the gradients explode. And well, you'll learn this in the quiz. Thank you.